Alright guys, welcome back. We're going to pick up our discussion of water properties today with this idea of thermal energy. And if we define just a couple terms here before we move on any further today, thermal energy, we're talking about the total amount of energy that is associated with the random movement of atoms and or molecules in a sample of matter. So how fast are these particles sort of flying through space is the thermal energy that they have. The more they're moving, the higher that thermal energy. The less they're moving, the lower. And we often end up measuring this via temperature. So a substance that is cold is going to have a relatively low thermal energy, and the movement of those molecules or particles is going to be relatively slow. The more we warm up that particular substance, the faster those molecules move, and so we see this as an increase in temperature. Water is going to be an interesting molecule because it's going to be able to absorb these super large amounts of thermal energy compared to another substance, and yet we're not going to see as drastic a temperature change on a thermometer as we would with some other substances. And this really comes down to the fact that in order to make those molecules move faster, I have to impart energy to them. And for water, because water participates in these hydrogen bonds, remember I said that hydrogen bonds have some energy associated with them. I've got to break those hydrogen bonds before I can get those water molecules themselves to start speeding up. Same thing happens in the reverse. I've got to get those hydrogen bonds to form before I completely am able to get those water molecules to slow down. So when we're measuring temperature on a thermometer, we're measuring the movement of those molecules, right? But before I can get those molecules to move, hydrogen bonding is going to add an extra layer to that in terms of the amount of energy it's able to absorb or release before I actually see a temperature change. And so we talk about this as specific heat. Water happens to have one of the highest specific heats of any substance out there. And so specific heat, we're talking about how much heat or how much thermal energy does a substance absorb or lose before that substance itself changes by 1 degree Celsius on a thermometer. And because water's polar, and because polar molecules have the tendency to have these intermolecular attractions, in water's case specifically the hydrogen bonding, polar molecules tend to have a higher specific heat because of those attractions between charges between molecules compared to something that's nonpolar, where the sharing of those electrons is equal, and so that nonpolar molecule doesn't have any regions of partial charge. So with water, I have to break those hydrogen bonds, then I can get the molecules to move faster, and then I'm going to be able to measure the temperature change on a thermometer. And something that's nonpolar, say like rubbing alcohol, all of that initial energy going in to warm up the substance immediately goes to making those molecules move faster because they're not having that hydrogen bonding going on. And so the temperature increase is going to happen much quicker in something that's nonpolar as opposed to something that's polar. So why does this matter to living things? Why is it actually important that it takes more energy to end up in water before the temperature changes? Well, there's a handful of different reasons why that's helpful to living things here on Earth. One of those is just general temperature regulation of ecosystems. So when we get these sort of coastal ecosystems that occur, whether they're coastal in the sense of being against the ocean or coastal being against some larger body of water, but not the ocean, so something like a lake or even bigger ponds. Sometimes you may notice this if you were a smaller organism. Those larger bodies of water are able to absorb and store all of this heat from the sun during the daytime, and also even more so during the summer, by But although they're sucking in all of this heat, all of this energy, the temperature itself of the water isn't going up crazy amounts of degrees, which is really important if you're an organism who lives in that water, because you're dependent on that water to sort of regulate your environment and even maybe your internal environment. So we don't want a couple of 90-degree, 100-degree days to go boiling off all of the water in a lake, because that would be bad for the organisms who live there. On the flip side, water in that case is acting as a heat sink. It's sucking all this extra energy off, keeps the coast cool, by the way. But the reverse is also true then at night and then during the winter time, where all of that excess latent heat that's now been sucked up by that water all day or all summer is now going to get distributed back on land. And so we end up with a warming effect at that point. And once again, what does this all end up doing overall? Regulates not only the water environment, but the coastal environment as well. And we see this even here. So I get that cooler air that comes off that lake, alright, warms up as it hits the coast, and we get these big convection cells that happen. And once again, all this ends up doing is ensuring that we sort of regulate the temperatures that are going on here at the coast. Which is why places like Southern California, right, pretty far south, alright, but they've got a pretty stable climate most of the year because they're getting ocean currents coming from places like Alaska, where they're bringing in this much cooler water, and that cooler water then is able to help regulate the land temperatures at that point. The opposite is happening in places like Great Britain, where they are much higher up in latitude, but have climate that's a little more similar to us, temperature-wise, because they get the Gulf Stream. So the warm water is coming up from the Gulf of Mexico, and they're benefiting from that regulation from there as well. Even individually as organisms, we benefit from temperature regulation, assuming our body is capable of doing something called evaporative cooling, and your body does. It's a homeostatic mechanism, it's a feedback loop. So what is evaporative cooling? Well, next time you're in gym class, this is probably going to happen to you if you're actually really kind of working out and working those muscles to the best of your potential. Evaporative cooling happens when your body recognizes that you're getting warmer. It's going to dilate your blood vessels, alright, get that blood as close to the surface as possible, and what do? You sweat. Okay? And those beads of sweat are mostly water, and they end up producing that water vapor on the surface of your skin. And the more and more that your body temperature continues to rise, the more and more your own body is actually going to cause that liquid water in that sweat sitting on your skin to evaporate. It's going to take energy from your body, right? Make the hydrogen bonds break, make those water molecules move faster, and go from a liquid state in the sweat to a gaseous state as it evaporates off your skin. And in the process of doing that, especially once you stop moving and your body temperature is able to start cooling down, well, why does it cool down? Because that sweat's still there, that evaporative cooling process is still occurring. And so we're taking that extra energy out of your body and pumping it into that evaporative process. And that brings your body temperature back down to normal and gets you back into homeostasis. So it helps you to maintain that natural body temperature that's necessary to ensure that you are functioning at a proper level at all times. While we're on the topic of phase changes, we might as well talk about what happens to water when it freezes. Most of us at this point probably should know that ice floats. Okay? Ice is the solid version of water, and it's kind of unusual that ice floats, because typically for most substances, their solid will contract, the molecules will get closer together, the whole substance will get more dense, and so that solid should sink in its own liquid form. And yet water does the opposite. When water freezes, rather than those molecules getting closer together, they actually expand and get further apart. And it's, once again, a byproduct of that hydrogen bonding. It actually forms these really expanded crystalline structures as opposed to really tight ones. So here's my ice, here's my hydrogen bonding structure, pretty far spread out, pretty expanded, less dense. I come over here to my water, and you can see that they're much closer together, considerably more dense. And so, what happens? Ice floats. Why is this a good thing? Well, if you're an aquatic organism that lives anywhere where that water can freeze at any point during the year, it's really kind of important for you. Because if, in fact, ice were to freeze and sink, that means that that lake, pond, whatever body of water we're dealing with would freeze from the bottom up. And if you're an organism, like our cute little shrimpy here, alright, eventually that ice would freeze and freeze and freeze and freeze and freeze, and you'd be stuck on the surface, exposed to the air, without any liquid water, and everything would be frozen. Okay? But instead, we get the opposite happening. So the ice floats, freezes from the bottom, from the top down. And so underneath, at the bottom of that lake or pond, you get these pockets of water that are now not only still liquid, but the deeper that ice gets, the more thermally insulated, the more heat insulation happens down here, and so the more stable the temperature of the water exists. And that's really good for these guys to ensure that they've got not only just liquid water to live in, but also a much more regulated temperature at which to live as well when it gets particularly cold out during the winter months. Alright guys, welcome back. We're going to keep talking about water, and if we're talking water, one of the things we really can't not talk about are mixtures, because when we talk water, it is rare to find water in and of itself hanging out on Earth. It's often part of a mixture, and a mixture is simply the combination of two or more substances that are not chemically united, but they sort of share the same space. Alright, so if we remember all the way back to when we started talking some of our review of basic chemistry, we talked about the difference between a pure substance and a mixture. So pure substances include things like your elements and your compounds, where no matter where I take it, from anywhere in the universe, that element or that compound is going to retain those properties. If it's a compound, it's going to be found in the same proportions, it's going to act the same way. Mixtures, on the other hand, don't really follow that process. In fact, I can take a mixture of sand, for example, even a couple of inches from each other, and the substances that make that up in terms of proportions may be slightly different from one another. So when we classify mixtures, we talk about them being either homogeneous or heterogeneous based on how the substances that come together in that mixture sort of share their space. So a homogeneous mixture, I'm looking at something that's got a uniform composition throughout its mixture, uniform appearance. We often refer to these as solutions. So if you look at a solution of salt water or mouthwash or black coffee, it's really hard for you to look directly at it and be able to pick apart the pieces because they're so uniformly spread out throughout that substance. Heterogeneous mixtures, however, or what you may have come across as suspensions in the past, these often are much easier to pick out the different components, figure out where they are at any particular point in time. So sand, if you were to look closely, or even do it under a microscope, you could see the different colors, the minerals and rock that make up that sand. oil and water, or think of salad dressings, a great example of heterogeneous mixtures, right? Especially something like Italian dressing, you can pick out the different herbs, you can see if you let it sit long enough, the oil and the vinegar separate, so on and so forth, so you can see those different particles. We're going to focus mostly on the solutions because when we talk water, water is sort of the quintessential solution maker. So a solution in and of itself, right, uniform mixture of two or more substances, it is a homogeneous mixture. And when we talk solutions, we've got two basic components or two basic parts to any solution, your solvent and your solute. And your solvent is the substance that's actually doing the dissolving, and typically is present in a higher concentration or a larger amount, as opposed to the solute, which is what is actually getting dissolved. So let's talk something like salt water, and water is your solvent. It's the material that salt, which is your solute, is getting dissolved into. Other examples, Kool-Aid, right? So water, once again, is your solvent. It's doing the dissolving of the Kool-Aid, which is your sugar and dye and flavoring that's in those packets, okay? And both of those happen to be specific examples of aqueous solutions, where water acts as the solvent. And we often talk about water sort of being this universal solvent. It dissolves a lot of different things, and rarely do we find water in nature not part of some sort of solution where it's acting as a solvent dissolving something else. So if water is in fact this universal solvent, then what does it dissolve and how does it work? So I'm going to throw a statement out there in a couple of slides, but I'll bring it up now. This idea of like dissolves like. So while water is a universal solvent, we know water doesn't dissolve everything. You stick water and oil together and they're not going to mix, they're not going to dissolve. But water's really good at dissolving a lot of different things. So while it doesn't dissolve everything, it dissolves a lot. And once again, this gets tied back to the fact that water has those slightly positive and negative regions of the molecule because it's a polar covalent bond that's holding those hydrogens to the oxygen. So water is able to dissolve anything that is like it, in the sense that it can dissolve anything else that also has some sort of charge associated with it. So one of the things that water is really good at dissolving are ions or ionic compounds. So something like sodium chloride, for example. So the ions in the sodium chloride come apart as water smashes into that salt crystal and yanks off individual sodium ions and individual chlorine ions, and you get dissolving happening like what's going on here in the picture. So water is going to brush up against this, either because it's just going to naturally happen because it's sitting there, or because you're heating it up and you're forcing these molecules to move faster, or you're stirring them and they're going to hit. And what ends up happening is that those individual chlorines and sodiums pop off of that original salt crystal, and they get surrounded by the water molecules because those molecules are attracted to the positive and negative ions. And in fact, if you pay really close attention here, and this is a really good thing to take note of, take a look at how that water ends up arranging itself around those different ions. Do you notice that it's different? Your chlorine ion is negative, right? And so opposites attract, even in this case. So you get those hydrogens which have those partial positive charges. That's what's going to be surrounding that negative chlorine, right? Positive and negative attract. The opposite happens to the sodium. Now I've got my slight negative charges from the oxygen, and that's what surrounds the positive sodium. Positive and negative attract. And so you end up with what we call hydration shields. That's what's going on here. And that hydration shield simply means that each of those individual ions, as they get yanked off that original salt crystal, get surrounded by water, and as a result, so long as that water is in place, that water is going to surround each individual ion and prevent those sodium and chloride ions from coming back together. Now, if you leave the water sit on the counter long enough, say a couple days, maybe a week or so, and that water starts to just naturally evaporate at room temperature, as those water molecules disappear, what do you get left behind at the bottom of the plate? But salt. Why? Because you're removing those hydration shields, and that sodium and chloride can come back together and reform the salt crystals. Now, water can dissolve anything that's ionic because of those ions having those charges. But compounds don't have to be ionic to also get dissolved by water if they themselves have partial charges to them. Something like sugar, for example, we also know gets dissolved. Why? Because it's polar. Alright, and anything polar means it's like water, which is also polar, and so they have those positive and negative charges, partial positives, partial negatives, to also get attracted to those water molecules, and something very similar is going to happen here, but rather than it being individual ions that get separated, they're individual whole sugar molecules that get separated and shielded from each other. So here's that particular statement. I want you to keep it in the back of your head. Say it over and over and over again to yourself. How do you know how quickly or how easily a particular solvent will dissolve a solute? Well, if you understand that like dissolves like, and you understand the chemical properties of the solvent and solute you're trying to put together, you should be able to determine whether or not those two things will readily mix together. So our concept or our topic here right now is water. So we're dealing with things that are readily going to dissolve in water or are not. And so there's two terms that we can utilize to describe how easily something dissolves in water, and those two words are hydrophilic versus hydrophobic. So anything that readily or easily dissolves in water is something that's hydrophilic. So they easily dissolve, which means they're like the water in terms of their chemical properties. So when we talk hydrophilic substances, these are things that are either ionic because they've got those charges, or they're polar, and so they've got those partial charges. Either way, those charges exist in that solute, which means they get to interact with the partial charges in water as a solvent. On the opposite side of that, anything that's hydrophobic is nonpolar. It's not like water in the sense that it does not have any partial or full charges to interact with those charges that are going on in the water, and so they simply don't dissolve in each other. Something like oil or fat, those are hydrophobic substances. They're nonpolar, they don't have any charge, and so they won't end up dissolving in water.